Hi everybody, welcome back to this course on internet technologies. I'm Vardan and today we'll be studying about web servers and network address translator. A web server is a software program that runs on a machine, often also called a server, and its job is to wait for requests from client devices, usually web browsers. When you type a URL into your browser, it sends an HTTP request to the web server associated with that domain. The server listens for these incoming requests and responds with the appropriate content, whether it's an HTML page, a CSS file for styling, a JavaScript file, or an image. Think of it as the host of a party. When guests arrive and ask for something, the host provides it. Similarly, the web server serves up resources on demand. There are many types of web server softwares, but some of the most commonly used ones are Apache, Nginx, and Microsoft IIS. These form the backbone of most websites, enabling everything from simple blog pages to complex web apps to function smoothly over the internet. A web server isn't just a file dispenser. It has some specific responsibilities to make web communication work. First, it must be able to receive HTTP requests from clients and send back responses. This includes supporting common HTTP methods like GET, used to fetch data or pages, POST, often used when submitting form data, and HEAD, which asks just for the headers without the full content. Next, modern web servers often need to run server-side programs like PHP scripts, Python web apps, or other executable code. These programs generate dynamic content based on users' input or backend data. After the program runs, the server sends the result, usually an HTML page, back to the browser. So whether it's loading a login page or submitting a comment on a blog, the web server plays a central role in handling these actions efficiently and securely. Every web server follows a certain directory structure to organize files and make them easily accessible. At the top, you have the root directory, which usually contains a folder named HTML. This is the document root, meaning any file inside can be publicly accessed via a browser. One key file here is index.html. When a user visits a website without specifying a page, for example, just typing in example.com, the server automatically looks for index.html and serves it. It's the default homepage of most sites. Then we have the assets folder, which typically contains subfolders like images and styles, used for storing images, CSS files, and other design elements. The conf directory holds configuration files that control how the server behaves, like the ports to listen on or how to handle errors. The CGI bin folder is where CGI scripts, executable programs, used to be stored. Even if CGI is outdated now, the server is still seen in many setups. Lastly, web apps might hold full web applications like admin dashboards or blogs. Keeping the directory well structured helps in managing content, troubleshooting, and scaling up the process when needed. Now, CGI scripts. Back in the early days of the web, one common way to generate dynamic content was using CGI scripts, short for Common Gateway Interface. These were server side programs, often written in scripting languages like Perl, Python, or C, stored in a special directory called CGI bin. When a user submitted a form, for example entering their name, the server would run the corresponding CGI script. The script processed the input, maybe looked up a database, and then returned a full HTML response. This worked well for a time, but CGI had some major performance drawbacks. Each request would start a new process, which would put a lot of load on the server and it made it inefficient for high traffic sites. As the web evolved, more efficient alternatives emerged like fast CGI, which reuses processes, and server side languages like PHP, or modern frameworks like Django or Node.js. These solutions are faster and better integrated with the web server, which is why CGI scripts are rarely used nowadays, except in a few legacy systems. Now, a little more on proxy server. Proxy server is a middle layer between client and actual web server. To the client, it acts like a final destination. To the actual server, it behaves like a client. This setup has many uses. For instance, a proxy can filter requests based on factors like client's location, the type of content being accessed, or even keywords. It can also cache frequently used content, improving load times and reducing bandwidth usage. Proxies often offer security benefits. They can hide the actual IP addresses of internal users or block access to certain sites based on rules. In corporate networks, proxies are often used to control and monitor employee internet usage. A reverse proxy works in the opposite direction. It sits in the front of one or more web servers and handles incoming client requests. It can distribute these requests to different servers, making it ideal for load balancing, SSL termination, or hiding internal server structure. Tools like Nginx or HapProxy are commonly used as reverse proxy in modern day servers. Now, network address translation or NAT is a technique used by routers to allow multiple devices on a private network to access the internet using a single public IP address. It was introduced to solve a major problem, the shortage of IPv4 addresses. Since we don't have enough public IPs for every device in the world, NAT allows homes and offices to use internal private addresses like one starting with 192.168 and share public facing IP otherwise. Here's how it works. When a device like your laptop sends a request to a website, your router replaces your private IP with its own public IP and keeps track of which internal device made the request. When the response comes back, the router looks up the mapping and forwards it to the correct device inside the network. In this way, NAT makes the internet accessible to entire networks without exposing individual devices directly. While both NAT and proxy servers sit between clients and the internet, they're fundamentally different in how they operate. NAT works at the network layer of the OSI model by modifying IP addresses inside packet headers. It does this silently without the client even realizing that any translation happened. It's fully transparent. On the other hand, a proxy server operates at the application layer. It actively interprets high level protocols like HTTP or FTP and may filter or modify requests based on their content. Proxies often require manual configuration on the client, such as entering a proxy address into the browser settings. Also, a proxy can cache web pages, restrict content, and log user activity, features NAT doesn't offer. While NAT is mainly about address translation, a proxy is more about traffic control and application level filtering. So, although they appear similar from a distance, they can serve very different purposes in networking. There are two main types of NAT, static and dynamic. In static NAT, there's a permanent one-on-one mapping between a private IP address and a public IP address. This is useful when a device inside the private network needs to be consistently reachable from the outside, like a web server or a CCTV system. The public IP never changes, so external devices always know how to reach it. In contrast, dynamic NAT uses a pool of public IPs and assigns them to internal devices on a first come first serve basis. So when a device inside the network makes an outbound request, it's temporarily assigned a public IP from the pool. Once the session ends, the IP can be reused by other devices. Dynamic NAT is efficient in terms of IP usage, but it doesn't guarantee a consistent address, making it unsuitable for services that need inbound access from the internet. The most widely used form of NAT today is NAT overloading, also known as port address translation. It allows many devices on a private network to share a single public IP address. But how does it keep track of which internal device made which request? That's where port numbers come to our use. When a device initiates a connection to the internet, the router assigns it a unique port number along with its public IP. This combination of public IP plus port is used to track the session. The router maintains a translation table, so when a response comes back, it knows exactly which internal device and port to forward it to. This method is incredibly efficient and it's used in almost every home and office network that comes to the internet through a single public IP. Let's see how NAT overloading works in practice. Suppose two devices on your local network, say 192.168.0.2 and 192.168.0.3, both open web browsers and make requests. Internally, they might both use port 4000, but when router sends their request to the internet, it changes the source port for each one. For example, the first device's request is written at public IP, then colon 6001. The second as 6002. The router keeps a translation table that maps these public facing port numbers back to the original internal IP and port number. When responses arrive at the public IP on port 6002, the router checks its table and knows to forward it to 192.168.0.3 on port 4000. This method allows hundreds of devices to use the internet simultaneously, all appearing to the outside world as if they're coming from a single public IP. This is an essential trick in a world running short on IPv4 addresses. While NAT is incredibly useful, it does have its limitations. First, it breaks the end-to-end communication model of the internet. Originally, every device was supposed to have a unique address and talk directly to any other device. NAT interferes with this by introducing an extra layer between them. Some applications, especially peer-to-peer ones like video calls, online gaming, or voice over IP services, can struggle behind NAT. They often need to use additional workarounds like stern or turn servers to establish connections. Hosting a service like a website or a game server becomes trickier too. Since devices behind NAT don't have public IPs, you need to set up port forwarding manually, mapping a port on the router to a device's internal network. This adds both complexity and security concerns. Finally, while NAT has helped extend the life of IPv4, it's not a long-term solution. It doesn't eliminate the need for IPv6, which restores the idea of unique global addresses for every device and simplifies many of the problems NAT tries to solve. With that, we've come to the end of this video, and that also marks the end of this portion of the Internet Technologies course about networking. And in the next portion of the course, we'll be understanding some security concerns of networking. So, thank you for joining in, and I'll see you next time.